This is the solution to random MathStat problem number 190. In this problem, we're given a random sample capital X1 through capital Xn from an exponential distribution with rate lambda. We're asked to use the Rao-Blackwell theorem in order to find an unbiased estimator for e to the negative lambda. Recall that the CDF for the exponential rate lambda distribution is given by 1 minus e to the negative lambda x. By inspection, it's easy to see that the probability that x is greater than 1 is equal to e to the negative lambda. There's no x in this problem, only an x1 through xn. Both capital X's that are on the slide now just represent generic random variables with the exponential rate lambda distribution. Let's actually look at our data points, capital X1 through capital Xn, to try to come up with an unbiased estimator for e to the negative lambda. Since e to the negative lambda is the probability that x1 is greater than x, we can make an unbiased estimator out of an indicator. The expected value of an indicator is always the probability of the thing being indicated, and in this case, we would get e to the negative lambda. So we have an unbiased estimator of e to the negative lambda. However, in this problem, we're asked to ensure that our estimator depends on all n data points x1 through xn. We're given the hint of using the Rao-Blackwell theorem, which says that we take an unbiased estimator and condition on a sufficient statistic. So let's find a sufficient statistic using the factorization criterion. The joint PDF for x1 through xn is a product of the individual exponential PDFs, and multiplying this out, we get lambda to the n, e to the minus lambda times the sum of the xi, and a product of indicators. We're looking for a pure x part with no parameter part of this PDF that actually doesn't even need to depend on x. It just needs to be no parameter. That's this part here. So we're going to define this to be h of x. Again, h of x could also be a constant like 3 and not depend on x, but the point is h of x is made up of the multiplicative factors in this joint PDF that do not depend on the parameter. The rest of the joint PDF we call g of s of x and lambda. This is the part of the joint PDF which is a function of the parameter and the data, where the data cannot be separated from the parameter by factorization. Note that this function g has a function of x plugged into it. That s of x is the sum of the xi's right here. The factorization criterion tells us that capital S defined to be s of the capital X's, which is the sum as I goes from 1 to n of the capital Xi, is a sufficient statistic for this model. Recall that we had an unbiased estimator t for e to the negative lambda. The Rao-Blackwell theorem says that if we define a new random variable t star as the conditional expectation of t given s, we have yet another unbiased estimator for e to the minus lambda. This will be a function of s. S is a function of all of the x's, so we will then have an unbiased estimator that is a function of all of our data points x1 through xn. Furthermore, the variance of t star is going to be strictly less than the variance of t, although that's not really our concern in this problem. To do such a conditional expectation, I find it convenient to start by fixing an actual value of s. Let's consider the expected value of t, given that capital S equals some little s. I'm going to plug in what t is. It's an indicator. And we know that the expected value of an indicator is always the probability of the event being indicated, even if we're in a conditional space where s equals s. You might think that this conditional probability can be computed by looking at the joint probability that x1 is greater than 1 and s equals s over the probability that s equals s. But for continuous random variables, this doesn't make any sense. The probability that s equals some particular little s is always 0 because there's too many possibilities. This numerator would also be 0 because we would have to have two events happen at the same time. One is that x1 would be greater than 1, and the other is that capital S would be equal to little s, and that can't happen with any positive probability. On the other hand, it is okay to have a continuous random variable equal to a value on the right side of a conditional line. We're always assuming that we can observe and measure our observations with infinite accuracy. So once you have observed that your capital S is equal to a specific value, it's okay to continue in that space where you're conditioning on S equaling that value. In other words, S equals S on the left side of a conditional line would give you a probability of 0 and isn't really useful, but S equals S on the right side of a conditional line makes sense. In order to compute this conditional probability, we're going to find the conditional PDF for x1 given S and integrate over all x between 1 and infinity. Let's find the PDF. By definition, this conditional PDF is the joint PDF for x1 and S divided by the marginal PDF for S. Note, however, that we can write the conditional PDF for S given x1 as the joint PDF for x1 and S divided by the marginal PDF for x1. Unraveling this equation, we see that the joint PDF for x1 and S can be written as the conditional PDF for S given x1 times the marginal PDF for x1. Let's plug this expression in up here. We now have that the conditional PDF for x1 given S is the conditional PDF for S given x1 times the marginal PDF for x1 over the marginal PDF for S. We know that x1 has an exponential distribution with rate lambda, therefore we know this PDF. We know that S, as the sum of IID exponentials, has a gamma distribution with parameters n and lambda, so we do know this PDF down here. It remains for us to find the conditional PDF for S given x1. Remember, this is not the probability that S equals S given x1 equals x, because that would be 0. It may be easier for us to first consider the conditional CDF, or cumulative distribution function, for capital S, given that x1 equals little x, because talking about probabilities is usually a little bit easier. Let's plug in the definition for the random variable capital S. If x1 is already observed to be lowercase x, then to observe the entire sum, capital X1 through capital Xn, being less than or equal to S, is the same as observing that the sum from 2 to n of the capital Xi is less than or equal to S minus x. On the right side of this conditional line, we have the random variable x1, which is independent of all the random variables x2 through xn involved in this expression on the left side of the conditional line. Therefore, this given information is useless. It does not affect what's happening on the left side of the conditional line, and we can drop it. Let's call this sum t. We know as a sum of IID exponentials, n minus 1 of them, t has a gamma distribution with parameters n minus 1 and lambda. If you think this should be the gamma distribution with parameters n minus 1 and 1 over lambda, you're not wrong. In this case, you are likely using a different notation than I for writing down this gamma distribution symbol. If I write down what I think of as the gamma distribution PDF, my lambdas are going to be your 1 over lambdas. Let's replace this sum with t. We now have over here a conditional CDF for S given x1 equals x. It's equal to an unconditional CDF for t evaluated at S minus x. To get to the conditional PDF from the conditional CDF, we're going to take the derivatives on both sides here with respect to S. On the left side, we'll get the conditional PDF of S given x1. On the right side over here, a derivative with respect to s will give us the PDF for t evaluated at s minus x. Going back to the conditional PDF we actually care about, the conditional PDF for x1 given s is the conditional PDF for s given x1 times the marginal PDF for x1 over the marginal PDF for s. Because this value, little s, is an observed value, we can assume it is observable. That is, we can assume that it's greater than 0. Because capital S represents the sum as I goes from 1 to n of the xi, and those are all non-negative values, so that sum can only take on non-negative values. And once we've observed it, we have a value, a number, and it has to be greater than 0. So let's assume this little s is greater than 0. Using the line at the top of the slide, I'm going to replace the conditional PDF for s given x1 with the PDF for t evaluated at s minus x. Again, x1 has an exponential distribution with rate lambda. Capital S as the sum of n exponentials has a gamma distribution with parameters n and lambda. And t as the sum of n minus 1 IID exponentials has a gamma distribution with parameters n minus 1 and lambda. Let's write this one first. Here is the PDF for the exponential distribution with rate lambda. I'm going to jump to the denominator and write the gamma PDF with parameters n and lambda. Note that because we've already established that our observed s is greater than 0, this indicator is going to equal 1, and so we don't need to write it. Using this denominator as a template for the remaining gamma distribution, I'm going to write the gamma PDF with parameters n minus 1 and lambda evaluated at s minus x. We can cancel a lot of things here to end up with the conditional PDF for x1 given s as n minus 1 times s minus x to the n minus 2 over s to the n minus 1, an indicator saying that s minus x is between 0 and infinity, times another indicator saying that x is between 0 and infinity. I think we can simplify this product of indicators. This product is going to be 1 if and only if both of these events happen. Rewriting the set of inequalities in the top line, this is equivalent to saying that x is between negative infinity and s, and x is between 0 and infinity. If both of these happen, both indicators will be 1 and the product will be 1. And this can be described with one single indicator because the intersection of these two events, where both indicators will be turned on and be 1, is the region where x is between 0 and s. In other words, the conditional PDF for x1 given s can be written like this. Our goal was to find this conditional expectation, which is equal to the probability that x1 is greater than 1, given s equals little s. Because capital S is the sum of capital X1 through capital Xn, if s, this value here, is less than or equal to 1, there's no way the first value in that sum could be greater than 1, and this probability will be 0. However, in the case where s is greater than 1, we get this probability by integrating the conditional PDF we just found from 1 to infinity. Let's do it. Here's the integral from 1 to infinity of that conditional PDF. We can pull out n minus 1. We can pull out the s to the n minus 1 in the denominator. And the indicator is going to cut off our limits of integration. Our integral from 1 to infinity is going to be cut off to be an integral from 1 to s. Note that it's important here that we have that s is greater than 1, and we are in fact in that case. This integral is a simple u substitution where we can let u be s minus x and then du is dx. Given the details of that simple integration, we end up with s minus 1 over s to the n minus 1. It might be hard to tell from my handwriting, but these are all lowercase s's. In conclusion, the Rao-Blackwell theorem tells us that t star defined as the expected value of t given s, where it's not given to be a particular value, but s itself is a random variable. This is going to be 0 if capital S is between 0 and 1. Otherwise, it's going to be capital S minus 1 over s raised to the nth power if capital S is strictly greater than 1. As a reminder, capital S is the sum as I goes from 1 to n of the xi, and this is our final answer. This is guaranteed to be an unbiased estimator of e to the negative lambda by the Rao-Blackwell theorem.